Hi, this is Jose Luis here, and welcome to another video on this series, Introduction to Parametric Modeling. In this video, I would like to make a super fun hands-on exercise, which is going to be how to reconstruct a terrain from an image of a height field. So imagine we have an image which is grayscale and represents how high or how low certain areas of the terrain are. We can actually reconstruct geometry with that volume, for example, by creating meshes or creating NURBS surfaces out of that. So for example, here, I'm going to start increasing this mesh, which I had flattened, but I'm going to start factoring it based on the image map that I have previously loaded into Grasshopper. And then at the same time, something that is going to be super easy to do is going to be to create isocurves, or to create all the curves that are the intersections with horizontal planes, and therefore be able to create like this kind of image that we will be able to project, which is going to be the height field. So the isocurves as if it was a map. Now we're going to do this with meshes because it's very interesting, it looks 3D, but for the isocurves part, the definition of the curves are not going to be great. So for that, I'm actually going to switch to creating this terrain also with a NURBS surface, so that when I do the intersection, the curves are much smoother and they look way more natural, because we're not cutting triangles, we're cutting an actual NURBS surface. And therefore, when I project that to the XY plane, it looks like a real topographical map, which is going to be super interesting. Okay? It's going to be a fairly simple exercise. It's barely 12 or 15 components, but it's more about the ideas that we're going to explore here that I would like to emphasize. Okay? So this is going to be really cool, especially if you're into landscape or video gaming or those kind of things. So bear with me, and let's first do some sketching and some diagramming to think through how are we going to approach this problem. Let's do this. This exercise is going to be super simple and super easy as well, because it's going to be just basically mixing everything that we know how to do at this point. So we're going to start imagining that we have an image, and that image has some kind of grayscale tones to it that represent how high a particular terrain is. And then given that, it's going to be as simple as we have done in the previous exercises, where we're going to basically sample that image with a grid of points. For each one of those points, we're going to fetch the brightness of the image as a value that is inside of the range from 0 to 1, so 1 being very bright and 0 being not so bright. And then we're going to take all those points and we're going to move them in a C-space at a value that is going to be a factor of that brightness. So I don't know, 5 times the brightness, 10 times the brightness, however much the scale of the terrain we want that to be. That will give us a cloud of points that are now somehow in 3D space. And then if we join those, if we reconstruct them with a mesh, we will get a mesh in 3 dimensions, with each one of the points representing the height of the terrain. At a secondary, after that, we will just do a very simple operation like we have done before. We will generate a set of parallel planes in C, and then we will cut the surface, we'll cut the mesh with those planes in order to create the contour lines of this terrain or of this landscape. And maybe, I don't know yet, but maybe after that, because these contour lines are going to be in 3D space, they're going to have different heights, maybe something that we could do is we could project them all together to the XY plane in case we need to print them as a map or something like that. One thing that I would like to do is, I would like to do this exercise reconstructing a mesh, but I would also like to make this exercise reconstructing a NURBS surface instead. And I would like to do that because you will see that the quality of how the contour lines are going to come up is going to be very different, but also the performance of the algorithm is going to be very different. So depending on what do we want to do with those ISO curves, then we will choose one method or the other. But I'm going to provide both options for you to choose and for you to learn more as well. So let's get hands-on. Let's go back to Grasshopper. The first thing we're going to do is I'm going to load the image that I want to bring in. So I'm going to go to parameters, input, and I'm going to drop my image sampler here. And then I'm going to double click on the image sampler, and I'm going to find in my computer this file that I have that is called the height field from TerraGen. This is a file that I downloaded from Wikipedia. Let me find that. Yes, exactly. If you Google height map Wikipedia, it's literally the first image that shows up here that was generated with a computer, so with TerraGen, which is a software for generating terrains, which is actually really, really nice. I've used it in the past. Anyway, so I'm going to use that, and I'm going to maintain that the domains are I'm going to scale the domain up a little bit from 0 to 10 so that the image is a little larger here on the Rhino space. Then what I would like to do is, as I have done before, I need to generate a grid of points to sample the image. Now, for the reasons that I'm going to explain very soon, in this case, I am not going to generate that grid of images by creating a square grid like I have done in previous examples. But what I'm going to do is I'm actually going to create a flat planar mesh that is going to have all these a control amount of squares in the U and V direction, and it will be that mesh that I will deconstruct to obtain the vertices that I will use for sampling. So I'm going to go to meshes, and I'm going to primitives, and I'm going to go for mesh plane. As I do mesh plane, you can see that the boundary is going to be the rectangle that describes the boundary of this surface. For that, I will need to create an actual rectangle. So let me create a rectangle which is going to be centered on XY, and then X is going to be 10 units, and then Y is going to be another 10 units. This takes a domain, but I'm just going to give it one number, and I'm going to get a rectangle that is this big, and I'm going to use that rectangle for the boundary. Then how many faces along the X and how many faces along the Y is going to be defined by this other parameter here that I have, and it's going to be the same in both directions because the image is square. Okay, so with that, what I have created is a mesh that contains all these vertices and all these faces, which is great. And then that is a very, and if I deconstruct such a mesh, then what I will get will be a grid of vertices that are going to be equally spaced. So in a way, it's a very similar process to what I did in previous examples with the grid. It's just that we're going to start with the mesh instead. This will have advantages that you will see very soon. Now, I have created my mesh, and then I am ready to sample each one of the vertices, to sample it with the image. What you can see is that the image is giving me RGB colors because I forgot to tell the image sampler that I only want the brightness. So I'm going to click on the brightness, and now I get values from 0 to 1. And then, in order to now recreate the mesh, all the points that I had below, what I'm going to do is I'm just going to move them up in the Z direction, an amount that is directly proportional to how bright those pixels are. We know that from the data. So the only thing that I need to do is, for example, let's say that I created directly a Z vector with these values, right? So if I do that, then I can now move all those vertices in Z that contain amount. And you can see that I already start getting an effect of, like, some points are going higher, some points are going not so high, all right? Which is kind of, it's starting to be pretty nice. I'm going to leave the mesh there, actually. And then what I would like to do now is, with these points that are above the mesh and that have been modified by the height field or the height map, what I would like to do is I would like to create a new mesh that has its vertices moved in 3D space, like with this logic. So the only thing that I need to do is I need to go to primitives and need to click on construct mesh. Construct mesh is going to require all the raw information that a mesh needs to be created, which is going to be a list of vertices. Those will be the vertices that I just created new, and a list of faces. And this, having a list of faces, needing a list of faces, is the exact reason why I chose to create the grid of points, in this case, from a mesh. Because since I created a flat mesh that already had the information for the connectivity of the faces, so it already had like all the quad faces and all the indices, this information would have been pretty difficult to recreate in order to make this mesh now. So because I already have it here, and because the topology, so the same points are going to be joined with the same points. It's just that I have moved them in the Z height, but they are going to be connected with the same quads. So that's why I can reuse this information. Is going to come in very handy now to just plug in here directly. And if I turn out the base plane, you can see that, ooh, very nicely, I have this mesh now that it's resembling this topography. Is that so? Let me crank up this. I'm going to do 50 and I'm going to turn off the points. And is this topography kind of looking like this? It looks like this area is more depressed. This area is more like a ridge here, right? It looks like there's like some mountains here, which kind of fits this. And this area is also higher. So this area is also higher here. So, ta-da! This looks like it's working. And if I bake it, and I do, for example, like an ice, what is it, like a render kind of view of this. Oops, sorry. You can see that this, you can already see how this mesh is kind of looking like this one here. So that's great. So what was that? 5 components that we used to generate a mesh with volume out of an image. I think that's pretty badass, if you ask me. Not because I did it, but just because, you know, I think it's actually, I actually think it's pretty cool. One detail we skipped through, we tiptoed over, was the fact that I have used the values of the brightness here right away straight, and therefore the maximum height of each one of these points is going to be 1. And maybe that's not what I want, because maybe I know how much a pure white value for this particular image is, for example, like 3,000 meters. If it's, I don't know if it's a mountain, whatever. So what I would like to do is I would like to factor this height by a value. So that, for example, if I know that the pixel with maximum brightness is 3,000 meters, then I can set here 3,000 meters, and then that will basically scale the whole terrain accordingly. So that's just going to be a simple multiplication operation, taking each one of these values and multiplying it by a factor, and then using that as the C value. With this, now I have a way to control the overall proportion of either absolutely flat or it starts growing into like a serious topography with serious mountains, right? So maybe we like something more like this. I don't know. That's one thing. The other thing is we are using meshes, and we also know that meshes give us the opportunity to color them, because they give us the opportunity to add vertex colors to each one of their vertices. So since we have the mesh, why not use this image also as a texture that we're going to apply to the image? So what I can do is here, when I construct the mesh, remember that I can plug in vertex colors. So what I can do is I can use the exact same image sampler, but I can copy and paste it. But now instead of using the brightness value, I'm going to double click here, and I'm going to take the RGB colors. Sorry, I pressed cancel. We're going to use the RGB colors so that we're going to use the RGB color so that I have a full RGB spectrum here. Because imagine, if I plug this here right away, what I'm going to get is, well, I'm going to get errors, that's for sure. So that's why, that's why I would like to take, instead, I would like to take full colors. So that's why I need to do another sampling operation. And if I plug this in here now, you can see that my mesh now actually does have the ridges and the valleys. They have them colored specifically for according to its height. So I'm going to bake this now, and as I do, I got my mesh there, and you can see that the higher points are white and the lower ones are black, which is also kind of cool, right? And you can imagine like a fly through here. You know, how cool is this, huh? All right. Okay, and the last thing that I would like to do with this mesh is we probably want to now do something where we slice this mesh with a lot of parallel planes in order to get the ISO curves that define the height of these meshes, okay? And in a very similar way as we have in maps. So let's take a look at how we could do that. As we have seen before, we could use the method of the bounding box and the planes, whatever, but I'm just going to keep it simple. So I'm just going to create a simple XY plane that is going to start at 0. I'm going to add a couple parameters. So for example, a value that is going to be, for example, ISO curve height. So how many, what is the distance between ISO curves? And I'm going to set this to a value, a fairly small value, 0.1. And for example, another one that is going to be number of ISO curves. And that's going to be, for example, 100. With this, what I'm going to do is I'm going to copy this plane 100 times, or however many times, at a distance that is controlled by this height. So I'm going to create a series of numbers that is going to start at 0, that is going to have, the step size is going to be how far away they are, the ISO curves, and the amount of values is going to be how many ISO curves do I have. That is going to give me a series of numbers that is going to look something like that. And if I now use that to create C vectors, I'm going to create all these C vectors, and I can use those to move the original XY plane, hence creating a collection of planes in 3D space, which I can obviously now take and use as the cutting planes for this mesh. So I'm going to take all these planes, I'm going to move all this logic somewhere, I don't know, I'm going to move it somewhere here, for example, and then I'm going to take this mesh and I'm going to section this mesh by all these planes. This is going to be very similar to what we did in the previous exercise when we did the slicing. So I'm going to go to intersection, mathematical, and I'm going to use mesh versus plane. I'm going to take this mesh and I'm going to cut it by all these planes here. And whoa, nice. Look, check that out. Let me hide the planes, but check that out. How cool is that, right? So we have now my image from the previous exercise. We have now the terrain, which is a mesh. We have now the terrain has been colored, and we have like all the ISO curves, which pretty much look like a plane, like a map, right? And if I actually turn off the preview mesh edges, so now you can see how we have kind of grouped similar colors with these cutting planes, and then you see that all this black area, and this white tips here. And I'm going to, and this is looking really, really cool actually. And of course, this is parametric, so I'm just going to move this to my other screen, and I can add less height between the curves. I can have more curves, etc. But I can do, for example, 0.05, and this is going to look very, very nice. Okay. All right. This is great. Now it's looking pretty good. Now, what do we want to do now? The last thing that I would like to do is I would like to take all of this and I would like to project them to the XY plane so that in case we need to laser cut them or in case we need to plot them or print them, they are all on the same plane and it makes things a little easier. We could also color them by height, actually. That could be interesting to do. But anyway, let's do that first. So what I'm going to do is I'm going to go back and dock my grasshopper here. And I'm going to take all the curves. And what I'm going to do is I'm just going to project them onto a plane. So I'm going to take all this geometry and I'm going to project that geometry to an XY plane. And if you see, and if I hide that, you can see that I have now created this projection that is planar, but it's on the XY plane and would allow me to print and to do whatever I want with this. Can you see? All right, so this is great. It's looking great. Yes, so I forgot to mention that this projection operation that just came out of the blue is actually part of the transformation. So it's not only Euclidean transformations or moving, rotating, but projecting things is also one of the transformations that we can do because they actually move them in space and sometimes they scale them, etc. So it's also part of the operations that we can do. And the last thing that I would like to do is I would like to highlight one property of this. So if you look at the isocurves that I have generated, turns out that they're not very nice because they're coming from a process that has suffered a lot of discretizations. So for example, a pixel image is already a discretization of reality. Meshes are also a discretization of reality because you take reality and you chop it in phases. And because phases are planar, turns out that we get a lot of situations where the curves, well, basically the curves are polygons. That's one thing to notice. The other one is that in many instances we have several situations where we have a lot of perfectly parallel lines because we have cut the same triangle by multiple planes. And we have these very abrupt kink corners, which they're not very nice. And look at this. If I zoom out, you can see how these patterns, these moire patterns, are arising because of these parallel faces. It's just not a very nice thing. So I may want, if I can, I may want to, for example, smooth out these curves. I may want to create curves that are actually curved and that they transition smoothly between all these planes, all these points of the polyline, so that the curves look a bit more natural because terrain is not just triangles in 3D space. Terrain is typically like made out of curves. So how could we smooth these isocurves in a way that it makes them feel a bit more natural? I see two ways around this. One could be the quick and dirty, which is taking these polygons and then basically for each one of these polygons creating a curve that is interpolated on each one of the vertices that forms that polygon. So if I have a polygon, if I have 4 points and I trace an interpolated curve between them, then I may end up with something that is a bit more natural. That's actually fairly easy to do. Here, if we do, for example, if I take all all the polylines that I have projected, and I can do this on the projected ones or I can do them on the ones in 3D space, it doesn't matter. But I can take the polygons that I have projected to the floor and then I can, for example, I can take this and I can explode each one of the polygons to obtain the vertices. So I'm going to take this, I'm going to explode them, and I'm going to obtain all the vertices for each one of the sections, for each one of the polylines. And as I do that, what I can do now is take each one of those lists of vertices, which are very conveniently organized in branches, and then I can just pass that by an interpolated curve, and the result will be something like this. So if I stop sharing, you can see that now the things, so if I overlap, you can see how from this polygon, now I have this kind of curve going on, and from this polygon I have this curve here as well. So it looks like, and from here I'm also getting this result, so it looks like it's kind of doing its job. So it's working pretty well. However, the problem with this approach is, well, it's not very exact, but honestly, given the whole process that we have followed, I don't think that any process would be very exact. But my main concern is that in areas where there's a lot of density of polygons, then these things are going to happen. What's going to happen is that because we have so much density, then some of the curves are going to overlap with each other. So for example, this is happening here because they are so close to each other, and this line is so big that the interpolation algorithm tries to smooth out, and it actually overlaps on top of the next one. This, to me, it's actually a big problem because this is very strictly wrong. If you're doing a map that has isocurves that represent differences in height, then having these curves overlapped is a tremendous mistake because it just cannot happen physically. So I'm going to propose an alternative method, which is the cleaner parametric method, which is that instead of relying, so for example, you see it's happening here and here as well, and here, is it happening? Yes, here, for example, we have another overlap. So I'm going to propose the following. I'm going to propose that instead of creating curves that are coming from the polygons that we generate from cutting the mesh, what I suggest is that instead of that process, which is kind of dirty, why don't we just, instead of creating a mesh in 3D space, instead of creating a mesh in 3D space, which is very nice for representation, etc., but for the sectioning, instead what we can create is an actual NURBS surface that already embeds and it's already infinitely smooth. And then it is that smooth surface that we create from the terrain that we section with the planes, and it's already going to give us smooth curves for this process. So how would we do that? Well, let's go back a few steps and go back to where we created the planar mesh that we then decompose into all these points. And then when we create another family of points that were the points that define the topography of the terrain. Then at this point, what we did was we reconstructed a mesh so that we could have some kind of geometry to see that form, and also because it was very nice to have the colors projected on the mesh. Don't get me wrong, that's actually pretty cool. But with these points, there are actually ways that we can use these points to recreate an actual NURBS surface. And this is because it turns out that these points actually do have, as opposed to meshes that come, for example, from 3D scanning, from other processes that are more involved with nature. But if you look at this, these points, even the modified ones, they have a fairly clean and cut logic, which is that they are laid out in XY with a particular direction of U and V. So it turns out that there are ways of reconstructing surfaces from a cloud of UV points that are nicely laid out in 2 dimensions like these ones, and then create a NURBS surface out of that. The way we can do that is if we go to surfaces, and if we go to, where is that? To freeform, you can actually see that I can create a surface. One of the options is to create a surface from a grid of points. So I'm going to place this here, and let's take a look at what the component is asking me. It asks me for the grid of points, and it asks me for the number of points in the U directions and the and whether if I want to interpolate samples or not. So I'm going to give the points here, and you can see that all the points are on the same list because of the double wire, but also if I look here, there are no branches, everything is on the same list. So that's a good thing. And then U is going to be the number of points in the U direction. We know that we divided the mesh in this many U points, So I'm going to plug this in here, and it did not work. It did not work because I did a tiny mistake, which is the fact that we need to read the fine print always, okay? The fine print is that U is telling me it's asking me for the number of points in the U direction. Whereas what I have done here is that 50, I have used it to define the number of faces in the X direction. And as we have seen in previous exercises, when I divide something in 3, 4, 5 spans, what I end up getting is 4, 5, or 6 points, or 1 more point than the amount of divisions. So what I need to do is just a simple rule here, where I'm going to add to this. I'm going to take this off. I'm going to add here the number 1, and then boom. And as I do that, you can see that now I have this thing that looks like, let me bake this to make sure that it's a surface. I'm going to bake this, and I'm going to move it all the way here. And you can see that, what? It's actually a real NURBS surface. It's not an actual, and if I click on it, it kind of looks like a mesh, but you can see that it's not triangles, that each one of the edges is actually a tiny curve. So these are basically the ISO curves of the surface, but they are not really faces. So this is an actual NURBS surface, albeit one with a lot of definition and where the polynomial is probably crazy to figure out, right? But yes, so that works. And if I actually click F10, you can see how many control points this surface has. This surface is probably really heavy in memory right now. Anyway, so what I can do now is I can use this surface that I just created to subdivide it with all these planes that I just created here. So how am I going to do that? So I'm going to section it with a mathematical intersection that is going to be B-reps and planes. So I'm going to place that here. The B-rep is going to be the surface that I just got, and the planes are going to be, if you remember, all those vertical planes that I created for sectioning. So I'm going to use those. I'm going to plug them in here, and you can see that compare how much more expensive to perform these sections is than doing it with meshes. Meshes and mesh geometry, in a way, it's very computationally lightweight. NURBS operations and intersections are way more complicated, more computationally intense, always. But if we look closely enough, you can see that the intersections are now very nice and very clean, smooth curves. And if I look from the top, you can see that it looks like way more natural than the situation that I had before. And of course, if I now project this to the XY plane, what I will get is this other form of height fields. So all these other isocurves that look way better than what I had before. So I had this, remember, the green is what I had, and the green is what I did from the polyline, and the red is what I just got from the NURBS surface. So you can see that I'm not getting kinks, I'm not getting this weird pointy here, I am not getting the crazy overlaps that I was getting here, I'm not getting, look at the difference in the shape, right? So how much nicer this is than the other. But you see, I'm starting to get errors here because NURBS intersections are not perfect. Sometimes they can be buggy. So you see, I'm missing this area here. I'm missing this part here as well. So yeah. So sometimes NURBS geometry is so complicated that sometimes it's even a little buggy. But I think with this, we are ready now to just send this to printing or send this to, I don't know. Where do we send this? Now, those are the pros. For the case of the isocurves, NURBS surface is a much better approach. For the sake of just perhaps 3D visualization and the coloring of the meshes, perhaps meshes are the way to go. I don't know. I think this is now at this point is up to you. And yeah, and I think that's everything that I wanted to do. So that's what I wanted to do for this exercise. And anything else that I'm forgetting? I don't think so. So if that's the case, then I think we're done with this exercise. This was reconstructing terrains from height maps or height fields. I hope, and we used two techniques, mesh reconstructions and NURBS surface reconstruction. So I hope this was useful, and I hope you now go ahead and take some images from the internet or some maps, whatever, and you try to recreate them in 3D. It's a lot of fun. You could also 3D print this mesh as well, even with the color, and that would be really cool. All right, so that was it. If you thought this was useful and if you like what you saw, maybe consider subscribing to the channel, liking this video, turning on notifications and all those things. And thank you very much. I will see you on the next videos in this series. Bye bye.